Watch an assembly line process objects one by one until it pushes past its structural limits and shatters into a synchronized grid. This transition illustrates the core shift that defined the last decade of AI research. We often describe the transformer as a new way to generate text, but the change was actually hidden in the mechanics of the computation. The generative engine inside modern language models is doing exactly what earlier neural networks did: autoregressive next token prediction. Given a context, the model calculates the probability distribution for the next token in the sequence. The mathematical goal remains the same. To find the actual innovation, we have to look at the previous standard for sequence data: recurrent neural networks, or RNNs. This timeline illustrates the structural dependency in recurrence. Because an RNN compresses the past into a fixed-size hidden state, it must process positions strictly in order. To calculate the representation for position t, the model must wait for the computation at position t-1 to finish. This creates a sequential chain where information is carried one hop at a time. This dependency caps how fast the model can ingest data. This sequential structure clashed with the design of modern hardware. Graphics processing units are massively parallel processors, designed to execute thousands of calculations simultaneously. When forced to wait for an RNN step-by-step updates, most of a GPU's processing power sits idle. The transformer architecture changed how that probability conditional is computed. It replaced the sequential recurrent chain with a system where every position looks at every other position in a single parallel operation. By computing the conditional probability through parallel matrix math instead of a sequential chain, the transformer removed the structural bottleneck that capped AI training. It allowed the math to finally align with the massive scale of parallel hardware. The mechanism that replaced recurrence is called self-attention. The goal of self-attention is to let every token in a sequence look directly at every other token simultaneously. This allows the model to learn which words are relevant to each other without compressing the past into a single vector. To calculate these relationships, the architecture uses a system similar to a relational database. For each token, the model generates three distinct vectors. First is the query, the specific context that token is looking for. Second is the key, a label broadcasting what the token offers. Third is the value, the actual information passed on if selected. This heat map represents a dot product operation. The model compares every query against every key simultaneously to calculate a raw similarity score. To keep scores from saturating the model, they are divided by the square root of the key dimension. A softmax function normalizes these into a probability distribution, the attention weights. Finally, these weights are multiplied by the value vectors and summed, creating a context-aware representation built from the entire sequence in a single step. In the sentence, "The animal didn't cross the street because it was tired," the representation for the word "it" will form a query that attends most strongly to the key for the word "animal." Because this happens in a single matrix operation, self-attention maps complex, long-range dependencies in a single time step, regardless of the distance between the words. But the query key value mechanism has an inherent blind spot. Because it calculates all relationships simultaneously, it is permutation invariant. It treats the input as a set of words rather than a sequence. Without an explicit marker for order, the math treats the sentence "dog bites man" identically to "man bites dog." This graph illustrates rotary positional embeddings, or ROPE. It injects order by rotating the vectors by an angle proportional to their position index. This mathematically separates identical words based on where they appear in the sequence. The model then runs several of these operations in parallel through multi-head attention. This allows different heads to track different linguistic relationships simultaneously. One head might focus on syntax, while another tracks semantic associations. This flowchart shows the assembly of a transformer block. The input flows into multi-head attention to exchange information, then into a feed-forward multi-layer perceptron. Holding 2/3 of the model's parameters, this layer acts as key value memory, retrieving factual associations. Everything is stabilized by residual connections and layer normalization, bypasses that prevent mathematical signals from vanishing as we stack dozens of these blocks. Each block takes an isolated word embedding and mathematically transforms it into a deeply context-aware representation. How these blocks are used depends on what the attention mechanism is allowed to see. In an encoder-only configuration, Every token looks at every other token in both directions. This bidirectional context is ideal for analyzing existing text, but it cannot perform open-ended generation because it relies on seeing future words that haven't been written yet. The generative models we use today use a different configuration, the decoder-only architecture. This diagram shows the causal mask. It is a square attention matrix where the entire upper right triangular half is blacked out, displaying mathematical zeros. This zeroes out future tokens, forcing the mechanism to pull information only from the current token and those preceding it. During inference, this enforces strict left-to-right generation, predicting one word at a time. However, during training, the mask allows the model to calculate the loss for every position in a document simultaneously. We can train on an entire sequence at once while still teaching the model to never peek at the next word. That specific alignment, sequential generation during use, but parallel calculation during training, is why the decoder-only transformer powers nearly every large-scale model used in practice today, from GPT-4 to Llama. This log-log graph charts error rate against compute and parameter size. It reveals that as datasets and processing power increase, loss drops along a predictable power law line. These scaling laws made model development forecastable. Before spending millions, we can predict exactly how capable a model will be. As models cross these scale thresholds, we see the appearance of emergent capabilities, behaviors like multi-step reasoning or coding that weren't explicitly part of the training goal, but appear as the average loss falls. But scaling this architecture introduces a scaling constraint known as the quadratic bottleneck. Because the attention matrix compares every token pair, memory and compute costs grow with the square of the sequence length. A 1,000 token document requires 1,000,000 comparisons. A 100,000 token book requires 10 billion, the ON squared cost. This quadratic growth limits how much text a model can consider before running out of memory. One solution is mixture of experts, or MOE. Instead of passing every token through one massive layer, a router sends each token to only a few expert subnetworks. This increases the model's total capacity without a proportional increase in the compute required for each word. We are also seeing the development of state space models, which use a reformulated version of recurrence. These aim to provide the parallel training of transformers with a constant inference cost that does not grow exponentially with longer documents. Generative AI remains an exercise in designing architectures that align strictly with the requirements of parallel compute. Whether through dense attention, through expert routing, or new forms of recurrence, the goal is to maximize the scale of the information the model can ingest.